let's get started. So we'll talk about Runahead execution today. It should be exciting to hopefully many of you. There you go. We fixed that. Almost. This was exciting to me for a long time. I did my PhD thesis on this topic. And this is a topic that was memory latency tolerance. This is the first lecture on memory latency tolerance. And we've seen some techniques to tolerate memory latency before, but we're going to cover some other techniques in the upcoming lectures. Well, I guess that's what we'll do, start memory latency tolerance. We've covered memory. You've seen the latencies involved in accessing memory. And a lot of computer architecture today, or processor design today, is about how to tolerate these latencies efficiently. And Runahead execution is one method of tolerating those latencies efficiently. Prefetching will be another method we briefly touched on, but we'll go into a lot more detail in the next few lectures. I guess before I move on, not all of you are here. I assume some of you are still working on the lab. Coming to lectures is still important. Are you guys all done with the lab? Because you're all here?
Extra credit.
Oh, extra credit. That's good. Well, I look forward to your extra credit assignment too. And you can do, for your extra credit, you can do much better than the. So, for example, if you want to improve the branch predictor, you can actually tell us that our branch predictor sucks, and you can turn in a better branch predictor. But tell us under what conditions your branch predictor works better. So we'll take that as extra credit too. I'm happy to enable you to explore your creativity in the labs, even though we may not specify it. Okay, the second announcement is lab. Well, I guess there are 3 announcements. That was one. The second is lab 6. Originally, we said it's due April 18th, right? So we're going to push that 2 days out. So it's going to be April 20th, which is Sunday. It's a Sunday, just like we pushed lab 5 out. So hopefully that'll give you enough days. And third is we don't have class this Friday since it's the spring carnival. It's an early spring carnival, isn't it? Yeah. Is it normally April 20th or April 19th, the week after? But anyway, we don't have class this Friday. But please check off your lab 5 on the Thursday lab or the Tuesday lab.
Wait.
Yes.
This week?
This week, yes.
There's no class either.
Oh, Thursday there's no class either?
Yeah.
Thursday spring carnival too? Okay. Well, if you cannot check off your lab on Tuesday, make sure you check it off next week. How about that? I didn't know that there was no class Thursday. I guess normally I don't teach Thursday, so I don't care if there's class on Thursday or not, but this time it did matter. Okay. Any questions? Should we jump into memory latency tolerance? All right. Well, I guess I'll give you more required readings too. This is a paper I had written. This is the first paper I had written actually in my career. I'll make you read that. It's a fun paper. It's still fun to me. The writing could be improved, but I think that's how it is. That's what you realize after a few years. That discusses Runahead execution. This is the second paper, which will talk about prefetching, and which we will cover in the next few lectures. So these 2 papers should give you a good idea of what we're going to talk about next. There are a bunch of optional papers, some of which we will talk about in today's lecture. You don't need to read them, but if you want to delve deeper into Runahead execution and latency tolerance mechanisms and some prediction mechanisms which we will talk about, this should be good reading. Okay, we're going to talk about tolerating the long memory latencies. And let me make sure that this is actually happening, and it is happening. And this is a form of latency tolerance, right? Memory latency is no different from any other latency, except it's long. And latency tolerance, we've already seen one method, actually multiple methods of tolerating latencies, but out-of-order execution was one method for tolerating latency, right? And you tolerate latency of multi-cycle operations by executing independent instructions concurrently. While you're waiting for the result of this operation, some other instruction that's independent of it can execute. That's how you tolerate latencies. You're overlapping multiple instructions, execution latencies. And memory latency is one of them. And you all know how the out-of-order execution does. It does so by buffering instructions to reservation station and reorder buffer. And we know the concept of the instruction window, right? The instruction window encompasses hardware resources that are needed to buffer all decoded but not yet retired or committed instructions. That's the reorder buffer. And everything else is associated with the instructions that are decoded but not yet retired. Reorder buffer entries, register file entries, store buffer entries, load buffer entries, anything that you can think of, reservation stations. All these instructions consume these resources. Some of them may not be loaded, load store queue entries, for example, and some of them do. So you need all of that hardware infrastructure to tolerate the latency. The problem is the instructions that have long latencies. If an instruction takes a long time to execute, you need a large instruction window so that the machine doesn't stall. And we've looked at this example before. If an instruction actually takes 500 cycles to service, and in today's systems, instructions take very long if they need to access memory. For example, in an old Xbox, the latencies were over 600 cycles, 600 processor cycles to access main memory. If this is the case, you need a large instruction window. And if you're actually super scalar, let's say you're fetching 4 instructions per cycle, and one instruction takes 500 cycles, then you need a 2,000 entry window to be able to not stall at all. Basically, we've discussed this before, so I'm going to give the answer. How many cycles of latency can out-of-order execution tolerate? Well, whatever the instruction window allows it to tolerate. Right? And if you don't have an instruction window that's large enough, you stall. Let's take a look at that stall. When a long latency instruction is not complete, it blocks retirements. It cannot retire, and nothing that comes after it can retire because, remember, the model is precise exceptions. We need to maintain precise exceptions. You can only retire an instruction only after it's complete. And you cannot retire any other instruction that comes after that. As a result, incoming instructions fill the instruction window. Reorder buffer, reservation stations, load store queue entries, register file entries. They all get filled with these incoming instructions. And once the window is full, the processor now cannot make progress at all. It cannot place new instructions into the window. This is called a full window stall. Basically, the window becomes full and the processor stalls. There may be other causes of stalls. For example, you may have lots of reorder buffer entries, but you fetch too many loads. You put too many loads into the machine. And the load buffer size is 24 entries. Reorder buffer size is 128 entries. And you've already fetched 24 loads, which means that you cannot fetch the next load because that will be the 25th load, right? You do not have enough load buffer entries. So there may be other stalls. But I'm generalizing everything with a full window stall. Assume that you have 128 entries for every possible instructions, let's say. Then you're limited by the number of entries you can support in the reorder buffer so that we can continue decoding. We're not going to get into other kinds of stalls. So modern machines try to optimize the size of these buffers instead of having a monolithic size for everything. Because remember, the store buffer is a very difficult buffer to design. If you actually have 128 stores, and if you actually need to search 128 stores in that buffer every cycle, that's a very expensive search in terms of both cycle time, hardware complexity, and power consumption. So what designers today do, they try to size those buffers such that they can get a good critical path, which means that usually the size of that buffer is smaller than the total number of instructions that you can have that is decoded but not yet retired in the machine. Which means that if you have too many stores in the machine that you're fetching in the program, you may stall before the reorder buffer is full because you're limited by your store buffer size. Anyway, let's take a look at full window stalls in this case. A full window stall prevents the processor from making progress in the execution of the program. Let me give you an example. Assume that you have an 8-entry instruction window and assume that all of the buffers are sized accordingly. Let's say you get this load instruction. It gets an L2 miss. It takes hundreds of cycles. And then you have a branch instruction that comes after that. And you predict that branch, something happens, and then you keep fetching these instructions that are independent of the load and the branch. Well, they're dependent on the branch in a control flow sense, but not data dependent on any of these instructions. That's why they're green over here. You keep fetching these instructions, and eventually you execute these instructions, but these cannot be retired, right? Because this load is still going on. It's taking hundreds of cycles. Now, the program counter is at this instruction, but you cannot execute this instruction because you cannot place it into the instruction window, right? Because your reorder buffer is full. You don't have enough resources in the machine to execute it. The processor stalls until the L2 is serviced. And long latency gadgets are actually responsible for most of those stalls, as I will show you later. But wouldn't it be nice if you actually fetch this instruction and execute it? Wouldn't it be extra nice if this instruction were actually an L2 cache miss? If this instruction is an L2 cache miss, you're only going to service that L2 cache miss after you service this L2 cache miss, because you do not have enough resources in the window, right? Whereas if you had a 9th entry in your instruction window, you would have been able to fetch this instruction, generate this L2 cache miss, and overlap the latency of this L2 cache miss with this L2 cache miss. Make sense? So one entry, one reorder buffer entry, one instruction window entry would have overlapped the latency of these long latency instructions. Because you do not have them, have the extra entry, now these latencies need to be serialized, because you cannot place this instruction into the window before this instruction gets out of the window. So that's what we're going to try to achieve with run-ahead execution. Somehow have this small instruction window, but recirculate the entries such that these instructions that cause long latency cache misses can get in and overlap their latencies and get out. And we'll see how to do that. But the goal is to not enlarge the size of the instruction window. We'll see that slide. But let's take a look at, I'm getting ahead of myself. Let's take a look at some data that shows cache misses are actually responsible for most full window stalls. This is data that I had collected a long time ago, 2002 now, on a Pentium 4-like processor simulator with this kind of cache, this kind of DRAM latency, aggressive prefetching. And this is data averaged across approximately 140 memory-intensive benchmarks. These were from a suite that were drawn out of all traces that Intel used at the time to actually design and evaluate their processors. And Pentium 4 was one of them. The Halo was the next one after that. But basically, this shows what fraction of the time is actually spent stalling in this kind of processor, Pentium 4-like processor. 100 is all of the time to execute the programs. The processor spends only about 32% of its time not stalling. It's doing something, computing. 68% of its time is spent stalling. Make sense? Not good, right? We do not want to have this, but that's the effect of memory latency on the program execution. And most of this non-stall time, full window stall time, most of the full window stall time is spent waiting for L2 cache misses. How many, basically, the way to collect this data is to look at all of the cycles that you take to execute the program, and look at how many times you have an L2 cache miss at the head of the reorder buffer that you cannot retire, that you cannot commit. So this is not good. Ideally, we would like to minimize this as much as possible. This will actually, just to fetch ahead a little bit, there was a question on last year's final that is related to this. I'll encourage you to go back and look at that. And we could put that on the homework, next homework. Okay, so how do we actually tolerate these stalls due to memory? How do we actually reduce this fraction of time that we're actually stalling for memory? There are two major approaches. Well, we could reduce or eliminate these stalls somehow, by prefetching, for example, or we could tolerate the effect of a stall when it happens. And these, the line between these are sometimes blurry. But for example, out-of-order execution tolerates the effect of a stall. It doesn't prevent the stalls, right? Well, in a sense, when you stall for a long latency cache miss over here, if you have enough window entries, you will tolerate the effect of the stall by overlapping other long latency cache misses with it. Right? That's a latency tolerance technique. There are four fundamental techniques to achieve these. We've seen actually two of them. Well, three of them, I guess. We've seen caching. Caching eliminates the stalls. Multi-threading. Multi-threading tolerates the stalls, but you need multiple threads to do this. Out-of-order execution tolerates the stalls just as we've discussed. Prefetching we briefly mentioned, but we haven't looked at. So we're going to cover that next. And many techniques have been developed to make these fundamental techniques more effective in tolerating memory latency. So we're going to take a look at run-ahead execution, which is a technique to make out-of-order execution even more effective. Actually, it's a technique by itself because it can be applied to in-order execution as well, as we will see. Let's take a look at these in a little bit more detail, pros and cons. I guess we should be pretty comfortable with the pros and cons of 1, 2, 3 over here, maybe not prefetching yet. But these are actually techniques that were initially developed in the 1960s, all of these techniques. Caching, you've seen the Wilt paper that I mentioned. This is widely used. It's a simple technique. It's very effective, as we've seen, because locality exists in many, many programs today. But it's inefficient and passive. Why is it passive? Because you need to remember the compulsory misses. Caching cannot eliminate compulsory misses, right? You need to have this good locality behavior. If your working set size is huge, again, caching may not be very effective. And not all applications or phases exhibit temporal or spatial locality. That's one downside of caching. You cannot eliminate misses if you don't have temporal or spatial locality. So this is a good technique that's been widely employed in processors, but it doesn't always work. In fact, you need to do more, basically. It doesn't get rid of all of the cache misses. Well, you will still have cache misses after this, basically. Prefetching, this was initially developed in IBM 36091, which actually had out-of-order execution as well. But this works well for regular memory access patterns, as we will see in the next lecture. Basically, how you predict the next access pattern before the processor actually accesses it. It's usually much easier to do that if the access pattern is regular. If the processor is accessing address A plus 2, A plus 4, A plus 6, A plus 8, ... It's easy to figure that out. If the processor is accessing addresses randomly, it's very difficult to do this. So irregular access patterns is difficult and usually inaccurate and hardware intensive, and we'll take a look at that too. Multi-threading, we've seen this, right? And this works well if there are multiple threads. If you have only a single thread, in a fine-grained multi-thread processor, you're actually getting 1/n of the throughput, right? As we've discussed, where n is the number of threads that you need to support. And people have actually developed techniques to improve single-thread performance using multi-threading hardware. So let's say you have fine-grained multi-threading engine. People have developed techniques such that to inject threads into the machine, speculative threads, helper threads, that can prefetch for the main thread, for example. We're not going to talk about that, and I encourage you to take SUM 42 next semester if you're interested in that. But people try to take advantage of this multiple thread hardware to improve single threads performance. Instead of running totally independent threads, can we actually construct a thread that can do work for this main thread that we really care about? And one idea is to construct a thread that prefetches for the main thread. Another idea is to construct a thread that actually predicts the branches in the main thread. It's pretty interesting, right? Another idea is to run two versions of the same thread, but one is going a little bit ahead of the other one, such that you can actually find these cache misses and find these branch predictors such that both threads can run faster. This is called slipstreaming, if you will. And this happens actually in car races, Formula 1 or NASCAR races. Two cars get really close to each other, and they drive very fast that way because one of them actually blocks the wind of the other one. As a result, both of them can increase their speeds. It's pretty interesting. It's kind of similar here. The analogy is slipstreaming. Okay, we're not going to talk about that. We'll talk about that in SUM 42. Out-of-order execution. This was Tomaso's algorithm that we've seen that was initially designed by that. Actually, initially it wasn't Tomaso. It was a different form of out-of-order execution. CDC 6600 had a different form of out-of-order execution algorithm. But Tomaso's algorithm was more elegant. This tolerates irregular cache misses that cannot be prefetched, right? It's difficult to basically. Well, I guess the out-of-order execution's biggest benefit is tolerating this kind of cache misses. Because if you can prefetch it in a simple way, it's great to have a prefetcher to do it. But if you cannot prefetch it, then your out-of-order execution is a good way to tolerate it. The problem is it requires extensive hardware resources for tolerating long latencies. And we'll talk about this in a second. The goal of Runahead execution is to alleviate this problem. Well, as we'll see in the current lecture, that needs to be fixed. Let me fix it. Okay. PowerPoint is saving that weird file that it renamed. There you go. So we'll talk about Runahead execution today. But keep in mind that Runahead execution alleviates this problem, but it can also be applied to in-order execution, as we will see. So I've already shown you this. Basically, if you have a small window, you get a full window stall. And you may not want to get a full window stall because if you had one more entry in your instruction window, you would have actually generated the cache miss for this instruction and overlap the latency of this cache miss with the latency of this cache miss over here, assuming they go to different banks. Again, you can exploit memory level parallelism, assuming that these accesses can be serviced in parallel by the memory system. That's why having multiple banks is very important. Okay, and I've already shown you that L2 cache misses are actually responsible for most full window stalls. In this case, for these workloads, the processor is stalling for about 55% of its execution time for L2 cache misses. There is a remaining portion over here. The processor still stalls these full window stalls. And the instruction at the head that cannot be retired is not an L2 cache miss, it's something else. Anybody guess what it could be? Like why these stalls exist? Floating point could be one of them, right? It could be another long latency operation. It could be a chain of long latency operations. That's why you may not be making fast progress. It could be a chain of L1 cache versus L2 cache hits, for example, because those could take long also. As a result, you may be stalling the processor even though you don't have an L2 cache miss outstanding. So if you actually do this, basically, ideally, design a 2048 entry window processor, this is what you get in simulation. This is nice. The execution time reduces from a normalized 100 to about 66, I guess, 68 maybe. So you get 34% performance benefit. And now the fraction of the time that this processor spends waiting for L2 caches is much smaller. Make sense? So ideally, we would like to achieve something like this. Our goal is to approximate the performance benefits of this 2048 entry window without actually having to build it. Because now you can imagine what's the complexity of building a machine that has 2048 entries in its reorder buffer, register file, load store queue, rename map, register alias table. Register alias table scales with the architectural register file, architectural register count, right? But its width scales with the entries in the window, right? But you still need reservation stations, 2048 entry reservation stations. Does this make sense? So it's difficult to build this machine, but we'll try to approximate the benefits of it. And I'll let you think about why this green actually grows. Any thoughts? So this green, with a 128 entry window, the machine spends this amount of time not stalling. With the 2048 entry window, the machine spends this much amount of time not stalling. Yes?
Because maybe some of them, because this one stalls so much, some of the green is actually computed while it's stalling.
That's right. That's one reason. Exactly. Yes. That's actually one good reason. Because there is some computation that's actually happening over here. The other reason is actually branch mispredictions too. So branch predictor is not perfect here. So non-stall time includes wrong path execution time too. You may be not stalling, but you may be doing useless work that's going to be thrown away. Okay, but in the end, it doesn't matter. By enlarging making the window 8x the size of the window that you have today, you can improve performance by about 34% on average across approximately 150 workloads. That's a strong result. Well, how do you actually achieve this? The problem is, let me restate it. Automated execution requires large instruction windows to tolerate today's main memory latencies. As main memory latency increases, instruction window size should also increase to fully tolerate the memory latency. And there has been a trend for a long time in computer architecture. The processor speed increased significantly. The memory speed did not increase. As a result, the memory latency increased in terms of the processor cycles, in terms of the number of processor cycles. Now this has been tamed a little bit because processor speeds are not increasing as fast, and memory speed is increasing. But still, the number of cycles needed to access memory is on the order of hundreds today. And going forward, we'll have electron non-volatile memory technologies in the future. Maybe we'll have longer latency memories attached to the memory hierarchies of today. So the problem is that building a large instruction window is a challenging task. Well, let me finish that thought. We'll have non-volatile memory technologies attached to the memory hierarchies of today. And the non-volatile memory technologies that we have today are usually long latencies. Imagine flash memory being part of your main memory. That's not today, because flash latency is very long. It's too long to actually be useful for main memory. But we'll talk about phase change memory or spin transfer torque MRAM, which have long latencies compared to DRAM. So if you have something like that, memory latency would increase a lot more going forward. The problem is building a large instruction window is a challenging task, especially if you would like to achieve all of these. Low power and energy consumption, short cycle time, low design and verification complexity. And we've talked about the complexity of, for example, tag broadcast, right? That tag matching logic scales linearly with the number of entries you have in the reorder buffer, and actually linearly with the issue width. Actually more than linearly with either of those. So if you actually increase both, you'll get quadratic increase in the size of this logic. And you get more than quadratic increase in the power and energy consumption of this logic. And cycle time similarly. You would like to be able to access the register file the physical register file or the reservation stations in a single cycle ideally, right? And if you increase the size to 2048 or 4096, now those structures become really slow. And design and verification complexity is another one. It's already very difficult to design an out-of-order processor with all of that complexity. If you actually increase the size of the window, now you need some cycle time, need some power budget. At the same time, be able to design and verify that processor in a reasonable amount of time. In fact, much of the processor design time today for an out-of-order processor is spent for the design and for verification and validation. It's approximately 30 to 40% of the time it takes to actually market a processor from start to market. So this is a big problem actually. This is one of the biggest problems that led people to design multi-core processors instead of trying to improve the performance of single-core processors. Okay. So this is the efficient scaling of instruction window size is actually one of the major research issues in out-of-order execution today. How do we actually make this a lot more efficient? How do we achieve the benefits of a large window with a small window, or in a simpler way? And how do we efficiently tolerate memory latency with the machinery of out-of-order execution and a small instruction window? So that's one idea that we've seen is memory level parallelism. Right? The idea was find and service multiple cache misses in parallel so that the processor stalls only once for all misses. So this is just a reminder. And this enables latency tolerance because now you can overlap the latency of different misses. And we see several techniques to generate multiple misses: out-of-order execution, multi-threading, prefetch. Now we'll see Runahead. The idea of Runahead is actually basically this. It's a technique to obtain the memory level parallelism benefits of a large instruction window without building that large instruction window. Basically, the idea is this. You keep the size of the instruction window the same as your baseline. You don't try to improve it. Instead, when the oldest instruction is a long latency cache miss in your instruction window, you take the checkpoint of the architectural state and enter Runahead mode, a special mode of processing. The checkpoint of the architectural state is the program counter and the register file. Actually, if you remember register alias table, you can take the checkpoint of the register alias table. And you never deallocate the checkpoint again until you exit this mode. In Runahead mode, this is a speculative processing mode. The processor speculatively pre-executes the instructions. I say pre-execute because it's going to execute them again later. The purpose of this pre-execution is to generate prefetches. You want to actually checkpoint the architectural state. We're going to use the out-of-order execution machinery to execute these instructions just to generate prefetches. L2 is dependent instructions. These are the ones that are actually causing the stalls. You don't want them to cause stalls in this mode. Basically, the processor marks them with a special bit called the invalid bit and drops them basically. Because the data is not going to come back for hundreds of cycles. The processor doesn't wait for them. It basically inserts a bit into the register file and inserts a bit and marks their result as invalid, and that invalid bit is propagated across instructions through the out-of-order execution machinery. Right? So all instructions that cause an L2 miss and that are dependent on an L2 miss know that they're dependent on an L2 miss. They're marked as invalid. And these instructions do not get executed. They simply get dropped from the machine. Well, I guess I don't need to write it down. I already said it. So, but all other instructions are actually executed. Right? And what you do is you actually, let me actually show this over here. So let's say you figured out the oldest instructions in L2 cache miss. This is a load into R1. And you have all of these other instructions that are waiting for it. The processor basically marks R1 as invalid, so in the register alias table. And as part of the value that is broadcast for this load, R1 is marked as invalid. You have invalid bits. And this instruction basically gets out of the machine. Now you created one space in the instruction window because you actually checkpointed the architectural state at the beginning. Now all of the instructions that are dependent on this load, let's say you have a branch over here that's dependent on R1, and you do something, this instruction receives that it's actually invalid because this load broadcasts its result and got out of the machine. And this branch figures out that it's actually invalid. Now this branch broadcasts, well, if it needs to. In case of a branch, you don't need to broadcast, right? You just need to figure out what to do with the branch. In this case, you do not know the result of the branch. It's invalid, so basically keep going with the branch predictor. And this branch gets out of the machine too. Now you've created two spaces in the instruction window. Make sense? So you keep executing other instructions. Instructions that are dependent on the cache misses are marked as invalid and dropped. But instructions that are not independent of the L2 cache miss, get executed. And if these are instructions that generate cache misses, they become invalid and they get dropped. And now you can move the instruction window. You can actually keep fetching new instructions because you're creating space in the instruction window by getting rid of instructions in the machine. The instructions that are valid get executed and they get out of the machine. The instructions that are invalid do not get executed, but they get dropped and they get out of the machine. Yes?
What if the valid ones are dependent on the invalid ones?
They become invalid, right? Because whenever an invalid instruction broadcasts its result, it broadcasts the invalid bit also. And that becomes invalid at that point. Okay?
So you latch on to the invalid ones.
Exactly. And then you drop them. Basically, the retirement remains the same. I'll show you an example. But so you keep feeding new instructions into the machine. That's basically the key idea. By getting rid of old instructions, not stalling the machine. Make sense? So that's the key idea. We'll take a look at how it operates in a slide, basically. And this mode ends when the original miss returns. The original miss is the oldest instruction that caused entry into this mode. And at the end of this mode, basically, the processor restores the checkpoint and resumes normal execution. What does that mean? Basically, the processor restores the program counter of this long latency cache miss, restores the register file at that point, and re-executes all of these instructions again. And hopefully, they won't cause cache misses. Let me show this pictorially. I mean, ideally, what we really want is perfect caches, right? The processor computes, it gets this load 1 instruction, let's say, it hits in the cache, and it keeps computing, it gets load 2 instruction, it hits in the cache, we never stop, right? Ideally, that's what we want. But with a small window, this is what we get. The processor computes for a while, it gets this load 1, it misses in the cache. The processor can continue fetching instructions for a while until its instruction window becomes full. But once its instruction window becomes full, it cannot continue fetching instructions. It stalls until this miss gets back from memory. Right? And then, once the miss is complete, the processor can keep retiring instructions and compute for a while. Compute meaning retire instructions. And until it gets a load 2 cache miss, after which the instruction window becomes full after a while. After that, the processor keeps stalling until this load 2 miss completes. Okay? In Runahead execution processor, we're going to try to use these stall cycles, not stall, but keep processing instructions. And the idea is, when you get this long latency cache miss, this load 1 instruction becomes the oldest instruction in the window at some point. At that point, you take a checkpoint. Remember, oldest instruction, it's easier to take a checkpoint when the instruction becomes the oldest in the machine, because you know that's not speculative. At that point, everything else before it is retired and nothing after it has been completed, or at least reported result to the checkpoint. So you take a checkpoint here, checkpoint the program counter, checkpoint the register alias table, and for some other things, as you will read in your reading, for performance purposes, like the return address stack and the global history register, because we're going to get back to this point. And the processor keeps speculatively processing instructions without stalling for long latency cache misses. It will still stall for other reasons, but not for long latency cache misses. That's called the Runahead execution mode. And the processor, during this time, reaches this load 2, because now it can fetch it instead of stalling, and can generate load 2's miss, because it can execute load 2. And this miss gets started servicing in parallel with the miss 1, load 1's miss. After a while, this load 1 miss returns from memory, and the processor flushes its pipeline and returns to the checkpoint, restarts with load 1. So at this point, load 1 hits in the cache because its miss just returned, and the processor keeps computing. After a while, the second miss completes, and by the time the processor executes load 2, load 2's request has already completed, and it's already in the cache. As a result, you get a cache hit. And you save cycles, because what you've done is essentially, instead of stalling over here, you pre-executed instruction and you pre-fetched this miss 2. Yes?
So is this kind of just like slipstreaming, but for a single core?
That's a good point. At some level, you could think of it that way, actually. You're slipstreaming within a single context.
Yeah.
You're checkpointing the architectural state, running ahead, and going back. Absolutely right. You don't need a separate context. You could have done this with a separate context. In fact, IBM Power 6 does that. IBM Power 6 implemented Runahead execution in that form. What they did was they had a two-way processor. Two-way meaning they had two thread contexts. And once you get a long latency cache miss, you actually launched another thread in the thread context that does exactly this. So that's how they tolerate the memory latency. That way, the benefit of that is you don't need to flush the pipeline, right, at the end. The upside of this is you don't need another thread context. Okay? That's the idea. So how do you actually support this? We'll talk about that, but let's take a look at the benefits of this. The benefits actually are multiple. Instead of stalling during a long latency cache miss, and I say L2 cache miss, but you could actually do this for L3 cache misses, or even an L1 cache miss. I'm not talking about an L1 cache miss, L2 cache hit, because these are relatively easily tolerated with a small window size. Right? It all depends on the latency. If the memory latency is 10 cycles, then you can have a small window and tolerate that latency, right? If the memory latency is 1,000 cycles, then good luck tolerating that with a small window. So instead of stalling during a long latency cache miss, you're pre-executing these loads and stores. And these loads and stores that are independent of the L2 BIS instructions generate very accurate data prefetches. And this is true for both regular and irregular access patterns. This is independent of the access pattern, right? You're really pre-executing the program. You're doing what the program would do or would have done, assuming it went through that path. That's why these are very accurate. Instructions on the predicted program path are also prefetched into the instruction or trace caches. We'll not talk about trace caches, but the model that we evaluate this on had a trace cache. And again, if you take Sum 42, you'll see what a trace cache is. And the L2. Basically, you get good instruction prefetching also. Yes?
If you have a program that's heavy on branching and loading, is it possible to contaminate your cache and actually decrease performance?
That's right. That's perfectly possible, actually. Because if you actually, what you're really doing, and that's true for a large instruction window also. Because what might happen is, what you're doing really is you're predicting the branches, and if your branch prediction is wrong, and the instructions that you're executing on the wrong path are fetching data that you're not going to use on the correct path into the cache, you may be polluting your cache, you may be evicting something from your cache that's actually useful for later. And we've actually analyzed a lot of those benefits in these papers. You can look at my thesis for that. And I can give you other pointers too. But it turns out, I'll give you the gist, for most workloads, it turns out executing on the wrong path is, like the memory references that you generate on the wrong path are usually more beneficial than harmful. Why? Because while you're executing on the wrong path, you're generating some memory references that are going to be useful for the correct path also. Some of them are useful, some of them are harmful, and on average, it turns out executing on the wrong path is useful. It's a pretty interesting topic, actually. How do you make wrong path even more useful? People have looked at that also. Okay, and the third benefit is the hardware prefetcher and branch predictor tables are trained using future access information. Now you got to be careful with this because you need to, what you're doing when you're executing in Runahead mode is you're really using future access information and training the hardware prefetcher and branch predictor tables. But you need to ensure that you're not polluting the hardware prefetcher and branch predictor tables as well. Okay, I'm not going to go into that in more detail. So let's take a look at the mechanism in a little bit more detail. How do you enter Runahead mode? Basically, you need to checkpoint the architectural state, register state, because you're going to go back. You need to have the state. At the time, this load instruction was actually at the head of the reorder buffer. You need to have the program counter, you need to have the register alias table. You need to ensure that no instruction deallocates the entries in the register alias table for that state. Basically, you need to have the register file state at that point, right? And also, you need to checkpoint some structures that are important for performance. These are for functional reasons, for correctness reasons, because you need to be able to get back, because you're going to enter the speculative processing mode. And for performance reasons, checkpointing the return address stack and global history register is a good idea. Because if you go back, you're going to actually predict some calls and returns later on, right? You don't want to pollute the state of the register alias table with speculative instructions. Similarly with the global history register. Global history register is important because it tells you this is the context at which I'm predicting this branch. If you actually speculatively execute instructions and polluted this global history register, once you get back, That's a totally different context. Okay, let's take a look at instruction processing in Runahead mode in a little bit more detail, and then we'll talk about exit from Runahead mode. Well, exit from Runahead mode is simple, basically. You restore the architectural state from the checkpoint. And you flush the pipeline, of course. It's like a branch misprediction, except the architectural state that you use for restoration is different, right? It's really associated with this load. Okay, let's take a look at instruction processing. The Runahead mode processing is exactly the same as normal mode processing, except for two main differences. And that's what makes this attractive, because it doesn't change a whole lot in the instruction processing engine. First, it's purely speculative. Right? Architectural, register, and memory state is not updated in Runahead mode. And you can ensure that basically by not updating the memory state, right? You don't commit results into memory. This raises the question, what do you do with stores? And we'll talk about that in a second. And the second is, L2 misdependent instructions are identified and treated, especially as I told you. Their results are not trusted. And we use this inval bit associated with each result to keep track of that. And we'd like to quickly remove them from the instruction window instead of waiting for them to complete. Otherwise, we'd be defeating the purpose. There are two types of results that are produced, invalid and valid. Invalid means it's dependent on an L2 miss, and you can distinguish a result status by adding one more bit to each result. Invalid results are marked using invalid bits in the register file and the store buffer, because you don't want to trust them. And they're not used for prefetching or branch resolution. Well, what does this mean, basically? If a branch's source register is invalid, you're not going to resolve that branch. Right? Then the question is, what do you do with that branch? Right? Well, one option is to trust the branch predictor, which is probably a good option if your branch prediction accuracy is really high. And that's what we have done. And that's what other Runahead execution implementations have done. How do you remove the instructions from the window? Let's take a look at that first. During the speculative processing mode, you take a look at the oldest instruction in the window, and it's examined for what's called pseudo-retirement. It's really not retirement, because you're not updating the architectural state. If you have an invalid instruction, it's removed from the window immediately. Its result is useless. Right? You don't even know the result. If it's a valid instruction, it's removed from the window when it completes execution or becomes invalid. These pseudo-retired instructions free their allocated resources, any kind of buffer entries, such that you can put another instruction, a new instruction to the machine. And these pseudo-retired stores communicate their data to dependent loads. So if you have a store in the machine that actually is pseudo-retiring, that's getting out of the machine, if you would like to do good Runahead execution, if that value is later useful for the prefetching of a load, you'd actually like to have that result communicated to the later load. So how do you do that? Normally this is done through the store buffer, right? But store buffer doesn't store the results of instructions that are not in the instruction window anymore. Normally what you do when you commit a store is write the results into the cache. Right? But we cannot write the results into the cache because cache is architectural state. You don't want to expose these results, these stores, because they're purely speculative. So we add a dedicated memory structure called Runahead cache, if you will. A pseudo-retired store writes its data and invalid status to this dedicated memory. And the purpose is solely data communication through memory in Runahead mode. Kind of like a register file, but it's for memory. A dependent load reads its data from this Runahead cache. And the key realization is that this does not need to be correct. You don't even need to do this. This is a performance optimization. So you can have a store instruction in Runahead mode, and it could be valid or invalid, it doesn't matter. What you could do is you could drop the store. Right? You could say, when I'm taking this store out of this machine, I'm dropping it, I'm going to forget its result, whatever its result is produced. It's okay, because this is purely speculative. This will not affect correctness. You're going to go back to the checkpoint and re-execute everything anyway. Doing so, it turns out is bad, because there may be later instructions that you get in Runahead mode, later loads, that may need that value, that may access the same address the store is storing to. That's the purpose of this Runahead cache. It's a small, extended store buffer, if you will, that actually stores the data of the stores that are pre-processed in Runahead execution mode. Does that make sense? Now you don't have to have this, again, this is a design choice. You don't have to have this special memory structure. You could actually modify the cache structure to achieve the same effect. For example, one thing you could do is you could write to the cache and say, oh, this is actually speculative. The result was produced in Runahead mode, right? Such that, and whenever an instruction executes, it checks whether the result was produced in Runahead mode. And if the processing is currently in Runahead mode, that's great, you can get that value. But if the processor is in normal mode, now you don't touch that value. Because that value was produced in Runahead mode and it is purely speculative. Yes?
You said that if an instruction is based on a load or a store that's missing, you just drop it, right? What if like a branch that comes after that or a load from a specific that comes after that is based upon those calculations? Do you just drop those also?
Exactly, yes.
Okay.
Exactly. And this is, I think, the branch. Basically, if a branch is dependent on a load value, it cannot be resolved, right? This is called a mispredicted, well, this is an invalid branch. If it's actually mispredicted, then the processor stays on the wrong program path until the end of Runahead execution, right? Because there's no way of knowing what the correct direction for this branch is, because you do not know the value this branch is dependent on. And it turns out this degrades the performance benefit of Runahead execution and out-of-order execution in general, right? In out-of-order execution, if you have a long latency load instruction that is branch dependent on it, the processor predicts the branch and you keep fetching instructions, and it takes a long time for you to figure out that you're on the wrong path, because the branch is dependent on a very long latency instruction. On the other hand, if you have a valid branch, you can resolve the valid branch and initiate recovery if the branch is mispredicted. So you can actually do branch misprediction handling in Runahead mode. Okay? Okay. Any questions? So the reading that I've asked you to do for this week actually discusses the processor implementation in a lot more detail than I have done over here. But I've given you the basics and fundamentals of how it works. So hopefully you'll enjoy the reading. So let's take a look at the advantages and disadvantages of this kind of mechanism. I've already given you a couple of advantages. It turns out this leads to very accurate prefetches for data and instructions at all cache levels. In fact, I don't remember it off the top of my head, but the accuracy is on the order of 96%. 96% of all of the requests, cache misses generated, are reused later on. It's very difficult to design a prefetcher that's that accurate, because this follows the program path. It's relatively simple to implement because most of the hardware is already built in. Right? You're really utilizing the out-of-order execution machinery and adding another checkpoint to it, and adding these inval bits, and adding this Runahead cache for store-mode communication. Compared to other pre-execution-based prefetching mechanisms, which we will briefly talk about, but I've given you the basic idea. The basic idea is you have multi-threaded hardware, and you launch a thread that actually prefetches for the main thread, like the slipstreaming idea that we've discussed. It doesn't need a separate thread context. It uses the same thread context as the main thread. Right? And you don't need to construct a pre-execution thread. By the way, you could do that kind of prefetching today on processors that have hyper-threading, as Intel calls it, or simultaneous multi-threading. Okay. There are a bunch of disadvantages and limitations which we will discuss and we'll try to solve also. Obviously, you're executing extra instructions, right? Because we're processing some instructions and we're reprocessing them. And you could actually be reprocessing the same instruction many, many times. As we've discussed, it's limited by branch prediction accuracy. And any kind of large instruction window machine is limited by branch prediction accuracy. Because you're fetching many instructions, and if your branch prediction accuracy is not perfect, you're fetching lots of them on the wrong path. We've discussed it many times. This is, I guess, an answer to the second part of your question. What happens if you have a load that's dependent on this cache miss? Right? And if this load happens to be a cache miss somehow, you later figure out, well, you cannot parallelize them, you cannot prefetch them. So if you're doing a linked list traversal, for example, if the first access is a cache miss, you cannot do the second access because you cannot generate the address of that second access. Too bad. We're trying to solve this problem actually. Any thoughts on what could the solution be? Yes.
Well, can't you also have a load target buffer or something like that?
Load target buffer. I see. So what you're basically saying is somehow
like
predict
load
the
address
value.
prediction.
Load address prediction. Exactly. Load address prediction. That's right. That's one potential solution. And we'll try to do that with one prediction mechanism that I'll describe later on. Well, actually, load value prediction. We're going to try to. Well, you could do it two ways, right? You could predict the value of the load that actually generated the cache miss, or you could predict the address of the load that actually has an invalid source.
Yeah, but in this case, we want to predict the address, right? Because we want to get it into the cache. We don't actually care about the value.
Let me show you
Okay, sorry.
the mechanism. You could do it both ways. You could do it both ways. It depends on which one you're predicting. If you're predicting the load that's dependent on the invalid load, you not predict the address. If you're you could alternatively predict the value that's produced by the load that's actually the ancestor, if you will.
Yeah.
And then implicitly you're predicting the address. Okay, so the other limitation is that the effectiveness of this is limited by available memory level parallelism in your program. So if your misses, long latency cache misses are far apart from each other in the program, this may not work, right? You may be pre-executing lots of instructions and not seeing any cache miss. Okay, we'll see that actually. That leads to inefficiency of the mechanism. And we'll talk about this later, but memory latency limits how long you can run ahead. Right? If you run ahead very short, so let's say it takes 500 cycles to service a load, and your run ahead execution interval is that 500 cycles, but you needed only 505 cycles, 5 cycles more to generate the next L2 cache miss. Well, too bad. You've executed all these instructions, and you flushed the pipeline after 500 cycles. If you had gone a little bit longer, then you could have prefetched that next L2 cache miss. But you're limited by this memory latency. That's the upside of having another context do this, right? If you have another context that actually does run-ahead execution, another thread that actually does run-ahead execution, you could keep going on run-ahead execution. And that's what IBM Power 6 and Sunrock did. They had another context. When they didn't have that context, they used the same context. Okay. Let's take a look at the performance of this. What is the performance improvement? I'll show you some results. These are actually in the paper also, but these were the suites that Intel used to design its processor at that time. So this gives you an idea of what kind of suites they used. These are the spec workloads. Standard Performance Evaluation Corporation actually publishes some workloads that all the processors are benchmarked with, and these were the CPU workloads, CPU-intensive workloads. Some web workloads, some multimedia workloads, some office productivity workloads, so Word, Excel are here, for example. Some server workloads are over here, like transaction processing. Some workstation workloads, for example, your Verilog simulations are sped up by this. Actually, Verilog was one of the example. Verilog simulator was one of the programs over here. It gets sped up a lot, actually. It is a memory bottleneck. But basically, if you look at this, I show you 4 processes, and this is the average across all of the suites over here. And this is micro operations per cycle on a 3-byte processor. And this is, so there are 4 different machines. One machine is a not state-of-the-art machine with no prefetcher and no run-ahead. The second machine is the baseline, which has a good, very aggressive prefetcher that we will briefly talk about. The third machine has only run-ahead execution, not prefetcher. And the fourth machine, the red one over here, has both prefetcher and run-ahead with some configuration. So the performance improvement, average performance improvement of run-ahead execution compared to the baseline, the good baseline with the prefetcher, is 22% on average. And you can see that sometimes, most of the time, the machine with just run-ahead is better than the machine with the prefetcher. But sometimes the machine with just the prefetcher is better than the machine with just run-ahead. That kind of tells, and the prefetcher in this case was a streaming prefetcher. It latches onto regular access patterns. And it turns out this suite over here has very regular access patterns. And you can prefetch them much more effectively compared to using run-ahead execution. So run-ahead execution has overheads also, right? You need to flush the pipeline. Actually, that was one of the disadvantages. That should have been one of the disadvantages over here. You need to flush the pipeline every time you do run-ahead. Okay, so that's one example. This is one result. The other result is how does this compare to a large instruction window? That was one of the things that was interesting, obviously, because we're trying to approximate the benefits of a large instruction window. We're not getting all of the benefits of a large instruction window, right? We're getting the memory level parallelism benefits of a large instruction window, because this is a purely speculative processing mode. We're not saving results. Run-ahead execution doesn't save any results that is produced during run-ahead mode. Whereas if you have a large instruction window machine, you keep everything in the machine, right? You keep the results. You not only tolerate latencies of long latency cache misses, but you tolerate the latencies of floating point instructions, any short latency operation, any L1 cache miss, L2 cache. So this is the machine that I showed you earlier, the good baseline, 128 entry window without run-ahead. And run-ahead execution buys you about 22% over here, I believe. And so it does better than a machine with 256 entry window. And it does close to a machine with 384 entry window. Make sense? So you get almost close to a window that's 3x the size, right, in terms of performance. But the efficiency is a lot higher because you don't need to build that large window. And you can read the paper for analysis of some of these benchmarks. Sometimes, for example, in some workloads, Runahead is not as good as, Runahead is better than a machine that has even a 1028 entry window, a 1024 entry window. Why? Because it's more important to run ahead and generate cache misses than have a 1024 entry window machine. Right? Because Runahead is very efficient at generating new cache misses. Okay. Any thoughts? All right. Well, I guess this is one of the things that I was going to discuss. When is maybe I'll let you think about this for a while. Runahead versus a real large window. When is one beneficial? When is the other? What are the pros and cons of each? Any thoughts? So Runahead is definitely not a large window, right? It's approximate the benefit of it. Yes.
Well, you said that even if you take the wrong path, those addresses that you generate hits for still benefit you in some way. Mm-hmm. Whereas if you're not doing it speculatively, you just generated a bunch of data that you don't need. So in the case that your predictor is really bad, maybe runaway is better because you can still benefit a lot from the mispredicted path.
Mm-hmm. But that's true for the large instruction window also, right?
Okay.
Yes, you had some idea? Or?
Maybe for the run ahead mode, you're executing instructions 2 times, and maybe for the when you have a large instruction window, you're not executing everything 2 times.
That's right. Exactly. So that's one reason Runahead could be worse than the large instruction window, right? Because Runahead flushes the pipeline and re-executes instructions many, many times, so it's energy inefficient in that sense. With a large instruction window, you execute instructions once, and as a result, you could be more efficient. A large instruction window still stalls. Actually, this was another reason why Runahead does better than, okay, if you look at here, it's more clear here. This is 128 entry window plus Runahead. This is a 512 entry window machine. And Runahead does better. Why? Because even a 1024 entry window stalls in this case. Because you have lots of cache misses that are dependent on each other. Whereas with Runahead, you don't stall. You keep going. You keep farther. I can give you some numbers actually. With the average number of instructions that are executed in a Runahead period, Runahead mode, is about 711 across all of these workloads. So it's much larger than a 512 entry window machine. Make sense? Okay. I'll let you think about this. You can actually have a long list over here. And this was part of the exam question, or final exam question last year. We can take a look at some of these graphs. Okay. I guess I'll leave with a couple of things and then we'll take a break. So Runahead is by no means just for out-of-order execution, right? You can have an in-order execution machine. We have no instruction window, but whenever you get a cache miss, you could go into Runahead mode. That's the idea over here. How does Runahead fare if you have in-order execution? And the mechanism is the same, exactly the same almost. In fact, you could say even simpler. So one thought we had at the time was, if you actually implemented in-order in an in-order machine and added Runahead to it, would it perform similarly to out-of-order execution? And the answer is no if you look at this. This is the performance of the in-order machine. This is in-order plus Runahead. So it buys you about 39%. And this is out-of-order execution by itself. So there's still a 30% gap between the, maybe more than 30% gap over here, between the in-order plus Runahead machine and the out-of-order machine. And this is the performance improvement Runahead execution gets on top of the out-of-order machine. It's a little bit different because these are run for a different length of instructions, different number of instructions. So the takeaway is, Runahead is beneficial on an in-order machine. In fact, it's even more beneficial, right? Because you get approximately 40% performance improvements compared to 20% performance improvements if you, when you add Runahead on top of out-of-order execution. Why? Because in-order machine actually has no latency tolerance at all. It's in-order execution. It stalls whenever you have a dependent instruction. With Runahead execution, you're tolerating the memory latency, so you get significant performance benefits. These are actually slides from, so Sun Rock was the first processor that implemented Runahead execution. And these were the slides presented by one of their architects in August 2008. They had an in-order machine, and they called it scout execution. Basically, you're scouting out and figuring out all of these cache misses, right? And this is an interesting graph because it shows the trade-off they made. This is their L2 cache size, split between 256 kilobytes to 64 megabytes. And this is normalized instructions per cycle, higher is better. And if you look at this, for a rock machine, in-order machine with 512 kilobyte L2 cache, Reddit execution, Scott execution buys approximately 40% performance. And if you actually implement Reddit execution on top of a machine that has 1 megabyte, it has performance equivalent to a machine without Runahead, but that has an 8 megabyte L2 cache size. So you can think of it as using Reddit execution to reduce space of the cache. Instead of implementing an 8 megabyte cache, you implement Reddit execution and save 7 megabytes. And here, this is actually across commercial workloads that they were interested in examining. A lot of online transaction processing and database workloads. This is Sun, right? They were doing that kind of processors. Now it's Oracle. They were bought by Oracle. And at this point, it actually buys 12 megabytes. So this is another way of designing machines, right? What do you actually, the mechanisms that you add to the machine enable you to save other things in the machine. And maybe add more processors. And that's the choice they made, actually. They implemented Reddit execution, got rid of some of their cache, and added more processors. Okay, I guess let's take a 5-minute break over here, and we'll talk about the enhancements to Runahead to try to solve some of the issues that we've discussed. So let's be back at, oh, that's a tough one.
It's 34 right now.
It's 34 right now at 39, but it's not 34 over there. That's 37. So 42 is good. Sure. All right, let's get started and cover some of the enhancements to Runahead. So we talked about some advantages and disadvantages. So let's try to alleviate some of the disadvantages of Runahead. So this was the required reading. But these are some of the recommended readings as to how to alleviate some of the disadvantages. I don't think I'll get a chance to cover wrong path events. I'll give you the brief idea, basic idea. So this is actually applicable to large instruction window processors. Branch prediction is a big problem, right, as we've discussed. And as you increase the size of the instruction window, this becomes an even bigger problem because the potential you can exploit with a larger instruction window is enabled by your branch prediction accuracy, right? If you're not predicting your branches correctly, you may be spending most of your time on the wrong path, especially if your branches take a long time to resolve. So one key question was, can we somehow figure out if branch is mispredicted before the branch gets resolved? If the branch is dependent on long latency instruction, let's not wait until that long latency instruction executes, but somehow predict that we mispredicted the branch. It's kind of cool, right? We haven't predicted it correctly. Well, we predicted it when we fetched it, but we're going to reevaluate that decision later on based on whatever happened in the machine. And the idea is, can we somehow find events that, if we see those events, we can tell with a good certainty that something went wrong. Some branch was mispredicted in the machine. And that was the idea of wrong path events. So there are several events, it turns out, that indicate branch mispredictions in the machine. One good event is dereferencing of a null pointer. So if you actually have a load instruction that dereferences a null pointer, you can guess that, oh, something went wrong in the previous instructions. Right? Or your program is wrong. Right? It's one of those. Or a fault happened in the machine, actually. These are all possible causes. But more than likely, it's really that your branch was mispredicted because that's a much more common event than either of the other two. And actually, if you have a bug in your program, you don't care, right? Because your program doesn't work. If you have a fault in the machine, then you care, but you may not be able to do much about it. But if it's actually a branch misprediction, if you actually hedge your bets in the machine that when you see a null pointer dereference by an instruction, you can say, oh, something went wrong. So I'm going to stop fetching new instructions. That way you can save energy, for example. Or you can say, something went wrong. I fetched an instruction that actually dereferenced the null pointer, speculatively. One of the previous branches must have been mispredicted. And then you can start recovery early for one of those branches. Okay. That's the idea of wrong path events. Another example of these events is you actually decode an illegal instruction. This happens on the wrong path, much more often than it happens on the correct path. Because if it's on the correct path, then your program is again wrong, right? Again, the other reason for this could be you have a fault in the machine. Some particles struck your machine, and actually one of the register values flipped. That's another reason why this could happen, right? But like, that's again much less likely than having a branch misprediction. So it's a good bet if you decode an illegal instruction that you're on the wrong path. Another is you have an address out of range exception when you access an address. These kind of things. The other interesting one is actually if you keep getting lots of mispredictions in a sequence, that's a good indicator that you may have mispredicted a branch earlier. Again, this is a little bit softer indicator, but still a good indicator. Because that could be usually due to two reasons. One is either you mispredicted a branch, and your branch predict is totally off now. You're exploring some paths that you've never seen before. Or you're really, really exploring some paths you've never seen before. Your program is going through a phase change. In either case, well, you're mispredicting some branches. Okay, so that's the idea of wrong path events. Can we somehow look at some illegal or unusual behavior and use that as a hint that one of the branches was mispredicted? What are those events? And how do you exploit this behavior? Well, it turns out how you exploit this behavior is a little bit difficult because once you actually figure out with some good certainty that something went wrong in the machine, how do you exploit it? Which branch is mispredicted? Is a good question. Then you'll need to figure out which branch is mispredicted if you have multiple branches in the machine. Okay, I'm not going to go over that in more detail unless we magically have some time at the end of this lecture. Well, let's take a look at some of the other disadvantages of random execution and try to solve them. There are three of them, limitations at least. One is energy inefficiency. We're executing a large number of instructions speculatively, and how do we actually curb that? So the idea is to do more efficient random execution. I'll talk about that. And these are some of the papers that are related. The second is what we discussed earlier. Basically, if you have a cache miss that's dependent on a previous cache miss, you cannot parallelize these cache misses. Because the second one needs the address, which has not been computed, because the first load instruction actually added cache miss. As a result, random execution is usually ineffective for pointer-intensive applications, linked list traversals, for example, tree traversals. So we're going to try to fix that problem a little bit. And the third one is what I discussed. When you have a branch that's mispredicted in run-ahead mode, and if that branch is actually invalid, depending on L2 miss, you cannot recover from that. But maybe you can look at some of these other things that are going on in the machine and use those as hints that this branch was mispredicted. So let's take a look at the efficiency problem in a little bit more depth. These are some of the workloads that we've tested run-ahead execution with. And I'm plotting here the percent increase in instructions per cycle performance due to run-ahead execution on the y-axis. These are the blue bars on the left for each benchmark. And this is the average over here. And the red bars show the percent increase in executed instructions compared to the baseline. So on average, run-ahead buys about 22% performance increase, IPC increase, at the cost of executing 27% additional extra instructions. This may be an okay trade-off, actually. But there are some workloads that a run-ahead cluster executes significantly more extra instructions on, approximately 60%. Performance benefits are not measured, right? It's about 5% over here. There's another workload where actually run-ahead degrades performance very little. Because, well, you should be thinking of why does run-ahead degrade performance? It could be pollution, right? It could be because you're flushing the pipeline once in a while, and you're getting no benefit. And there's a significant number of executed instructions, like you get 50% more instructions. This is not good, right? And there's another workload where run-ahead gets a lot of gains, performance gains, approximately 110% over here. But run-ahead calls the execution of 235% extra instructions. So you get a lot of gain, but you also execute a lot of instructions. Now the key question is actually, how do we actually get the benefits that run-ahead execution gets without executing so many extra instructions? So we'll try to achieve that. We've actually talked about a couple of these at a different level. But there are three causes of inefficiency in run-ahead execution. One is short run-ahead periods. We haven't talked about that as much. The second is overlapping run-ahead periods. And the third is useless run-ahead periods. Let's take a look at what these are. Short run-ahead periods are run-ahead periods where you enter run-ahead mode and you exit relatively quickly. instead of 500 cycles or 1,000 cycles, you stay in run-ahead mode 10 cycles or 50 cycles. Now you don't want to do that, right? Because if it's only 10 cycles, probably your instruction window can tolerate that latency. So these can be caused by multiple things. Because you can go into run-ahead mode, your oldest instruction is an L2 cache miss, but it's already an outstanding L2 cache miss. Okay. Instead of 50 cycles later, this L2 cache miss will complete, and you will keep going, keep executing instructions. It could be an outstanding cache miss because it could be generated by the prefetcher, it could be generated by the wrong cat, or a previous run-ahead period. So this is the idea. When you get an L2 cache miss, you go into run-ahead mode, and then you enter, let's say you generate another L2 cache miss, and this starts getting serviced over here. Later on, you get out of run-ahead mode because the miss that caused entry to run-ahead mode got complete. You flush the pipeline. Mode 1 now hits, and later on, when the processor actually executes mode 2 again, it gets a cache miss again. Why? Because this miss has not been completed yet. The previous run-ahead mode started, but it didn't complete it. As a result, the processor enters run-ahead mode for a really short time. Now, you'd like to ideally avoid this run-ahead mode, right? Because you can tolerate this latency, perhaps, with the instruction window. Or maybe it doesn't matter, because if you run ahead only by this much, you'll execute very few instructions, and you're not going to get to the next L2 cache miss. And that's the idea here is to detect these periods and get rid of them. So these periods are bad. These short run-ahead episodes or periods are bad because they're less likely to generate useful L2 misses because you're not running it far. And they also have high overhead due to the flush penalty at the run-ahead exit. If you look at this, the amount of time you spend flushing the pipeline is very close to the amount of time you actually ran ahead. Okay. I'm not going to give you the solutions to this. The paper actually, you can imagine some solutions, right? You can actually say, you can actually look at how long the miss has been outstanding, for example, when you're considering entering run-ahead mode. If the miss has been outstanding for a long time, maybe you say, okay, we'll not enter run-ahead mode for this load instruction. You could do even more sophisticated techniques, but let's not go into that. But actually, if you do those techniques, if you do some of those techniques, you can get rid of these periods relatively easily. The second cause of inefficiency is overlapping run-ahead periods. And these are run-ahead periods where these are two run-ahead periods that execute the same instructions, or almost the same instructions. Let me give you an example. These are usually caused by dependent misses. So let's say you enter run-ahead mode due to this load 1 miss. You execute in run-ahead mode, and you have a load 2 that's in and out because its address is dependent on this load 1. You exit run-ahead mode. Later, you execute load 2. Now you can compute the address of load 2, and it misses in the cache. It's a long latency cache miss. And you do run-ahead execution on that one. If you look at these two periods, the instructions that are executed after load 2 in the first period overlap with the instructions that are executed at the very beginning, for a long time perhaps, of the second run-ahead period, right? Because these are starting from load 2. Now there may be differences because branches may be predicted differently, but many of these could be the same. So second period is usually inefficient. Actually, it could actually lead to new cache misses because now you have another value that's available, which is the value of this load, right? But more often than not, it's inefficient. Okay. Again, you can think about solutions to fix this problem, and the paper that I recommended to you provides a solution, but I'm not going to go into that detail. But we'll actually see a solution later on today. The third problem is periods that do not result in prefetches for normal mode. These are actually periods that are kind of useless otherwise, right? If you look at this, let's say you enter run-ahead mode with load 1, you run ahead, you exit, good for nothing. Because there's no cache miss that is generated during run-ahead mode. So these actually exist due to the lack of memory level parallelism. And you could eliminate these run-ahead periods. I'll talk about a very brief mechanism over here. You could predict if a period will generate useful L2 misses, right? And you could have a predictor designed for this purpose. I'm not going to go into how you actually design this purpose, but actually useless period predictors designed for this purpose can be very effective. You could actually have program hints that could tell you. Somehow, if you can say, oh, this is a part of the program where you won't see a lot of cache misses, if somehow that's accurate, you could use that to guide Runahead execution. And actually, that was one of the solutions that we've explored. But that requires some support from the software. But you could actually have a hardware predictor that does this also. Okay, so I'm not going to give you the solutions, the exact solutions. But if you actually figure out all of these problems and actually devise solutions to each of them, this is what you get. You can reduce the additional 27%, well, 26.5% extra instructions to 6.2%. While preserving, well, and these workloads, this was a workload that was not gaining a whole lot. We reduced the extra instructions that are executed to Runahead. While preserving most of the performance benefits of Runahead execution, right? Instead of getting 22.6%, now you get 22.1% by getting rid of these inefficient periods. Make sense? So whenever you design a technique that's effective, it's always important to think about how to make it more efficient. These are techniques that do not make the Runahead execution more effective, although they do have the potential to. By getting rid of some of these short periods, you're improving performance as well, right? Because you're not flushing the pipeline anymore as much. But on average, it turns out they're not making the Runahead execution more effective, but they're making it a whole lot more efficient. Instead of spending more than 25% additional instructions, you're spending only 6% additional instructions. Okay. So when you go out and design techniques like this or some other way, always think about efficiency as well, because additional instruction is always power in this case, or inefficient mechanisms are always costing you power. Okay. So Runahead execution, one big characteristic of Runahead mode is it's purely speculative, right? You can do anything over there, and it won't affect correctness as long as you design that period to be purely speculative. None of the results that are executed, that are generated during Runahead mode is reported to software, because the real architectural state at that point is the checkpoint. You're going to restore the checkpoint once you get out of Runahead mode. How do we achieve this goal? The goal is really to find and generate cache misses that would otherwise stall execution later on. Right? That's what we're trying to do. How do we achieve this goal most efficiently and with the highest benefit? And one idea is to find and execute only those instructions that will lead to cache misses. If you think about it, when you're doing Runahead execution, we're executing everything in the program, right? Some of these instructions may lead to cache misses, may lead to the generation of address, but some of these instructions are kind of used for other things, right? They never generate addresses. They never lead to the generation of addresses. Ideally, you would like to find only those instructions that lead to the generation of addresses, and in particular, the generation of addresses that cause cache misses. If you can somehow identify this, you can make Runahead execution even more efficient. How is the question, but I'm not going to answer that. But this is something good to think about, because if you could do this, then you could solve a lot of the memory latency tolerance problems. But one idea could be, for example, the compiler or the hardware somehow generates a thread that's specially constructed for Runahead execution. And when you get a low latency cache miss, you fetch from that thread and execute that thread. And that thread only does things that will lead to cache misses. It won't do the floating point operations that are not going to lead to cache misses. Right? Because usually you perform some operations on an array that have nothing to do with the computation of an address. That thread is specially constructed just to prefetch data. That could be a helper thread. That could be a Runahead helper thread. How to do this? Actually, this was an idea that Intel had published in 2004 in an Itanium processor. What they did was they called this the virtual multi-threading. And when the main program stalled for a long latency cache miss, they switched in a thread that was constructed exactly like this that did prefetching for the main program. So if you think about it, it's kind of like Runahead. You're not using the main program, the entire main program, to execute instructions and do prefetching, but you're generating this helper thread that is switched in when the main thread stalls. Does that make sense? Pretty interesting, right? You could go crazy with all of these ideas. And they've demonstrated benefits from that. The upside of that is now you can be a lot more efficient, because that thread can be constructed in such a way that it only executes instructions that lead to cache misses. The downside of that is you need to construct that thread. And how to construct that thread is actually not that easy. The upside of Runahead execution is, well, you don't need a thread. You just use the main program and keep executing it. It's simple. The downside is it's not as efficient as constructing a thread. Okay. So let's take a look at the dependent cache misses problem, and if we finish it early, I'll let you out early this time. So the second problem, the third problem, we've talked about irresolvable branch predictions a little, energy inefficiency, and ineffectiveness for pointer-intensive applications. Let's try to solve that problem. So let's take a look at the problem. The problem is you have a load 2 that's dependent on load 1. Load 1 causes entry into Runahead mode. Load 2 is executed through Runahead mode or fetched. And you figure out that it's actually invalid, and the processor cannot compute the address of this load 2. It keeps running ahead, and later on, it exits Runahead mode, and it executes load 2 because the value of load 1 is available at the end of Runahead mode, and it figures out that load 2 is a cache miss, low latency cache miss, and it enters Runahead mode again. So as you can see, Runahead execution cannot parallelize dependent misses because it doesn't have the value for this dependent cache miss. This leads to wasted opportunity to improve performance. Because if you had actually parallelized, you would have improved performance. You didn't need to go into the second Runahead mode. And it leads to wasted energy because the second Runahead mode is really overlapping with the first Runahead mode, right? And we've actually done some studies. This is the beauty of using high-level simulation. You could actually change your simulator and say, model Runahead execution in your simulator and say, if I get an invalid load that is a cache miss during Runahead execution, I'm going to magically say it's actually a cache hit, and I'm going to model everything as if it's a cache hit. Okay. That's the beauty of high-level simulation, C-level. You can do that. And we did that for many workloads, and we found that if you actually did that magically, the loads that are executed in Runahead mode that would have caused cache misses are actually turned into hits in the simulator. If you do that, performance would improve by 25%. Now the key question is, how do you actually approximate that 25%? So I'll tell you one method. Basically, the goal is to parallelize these dependent cache misses. We'd like to enable the parallelization of those cache misses in Runahead mode with a low-cost mechanism. How do you do it low cost? And we briefly discussed this earlier, but we'd like to predict the values of L2 address loads. And I'll tell you what these are, or pointer loads. Because this is really loading a pointer, right? If you think of it. Or at least it's loading something that you compute upon, maybe, that later leads to the address of this. It's loading the base of some pointer. Okay. So we'd like to predict the value of this, such that we can execute this. An address load is a load that loads an address into its destination register, which is later used to calculate the address of another load. Think of this as opposed to a data load. A data load doesn't lead to the generation of addresses later on. You can read this paper for a lot more detail, actually. But the problem was this couldn't compute its address. If we actually predicted the value of this load, now we can use the predicted value to compute the address of load 2. And assuming the predicted value is correct, at the cache block level at least, now you could start this miss, and you could parallelize that miss, and both of the loads hit when you exit Runahead mode, and you can save cycles. Make sense? That's the idea. So how do you do that? Now you also save speculative instructions as well because you don't enter Runahead mode again. Right? How do you do that? You could actually do that with different mechanisms. One option could be predict the value to be 0. Right? If it's an address load. Well, that doesn't work too well. Usually pointers do not have base addresses that are 0. That may work for other kinds of things. For example, if this load is actually feeding a branch that is mispredicted, if you predicted the value to be 0, and 0 happens to correctly resolve the branch, then you can improve performance. Well, you really want to predict the address of the second load somehow. And it turns out, we'll try to do what's called AVD prediction. And I'll give you, as if I knew all of this before, but this came out after analysis of many programs. So let's define the address value delta of a load instruction as this. AVD equals the effective address of the load minus the data value of the load. For some address loads, for some loads that load a pointer into their destination register, this AVD turns out to be stable. And the idea is to design a predictor that keeps track of this AVDs of these address loads. When a load is an L2 in Runahead mode, it consults this AVD prediction. If the predictor returns a stable, confident AVD, the predictor says, oh, the last few times I've executed this load, I've seen that this effective address minus data value is constant. If that's the case, the predictor predicts the value of the load like this. You know the effective address of the load, because that's the load that caused entry into Runahead mode, or that's the load that caused the cache miss during Runahead mode. You predict the AVD. Now the predicted value is effective address minus predicted AVD. Make sense? Assuming this is stable for that load. Kind of magic, right? Like, why would it be stable for loads? Now I'll give you the reasoning behind the magic also. But this is, I'm giving you as it was developed, because what I found out was when I was looking at this problem, I've listed a bunch of values and addresses and a bunch of other things about each load. And I've, by coincidence, found that the address value delta of some loads are actually the same across a large number of executions. So why would that be the case? It turns out these stable AVDs occur because there's a lot of regularity in the way data structures are allocated in memory and traversed. And I'll give you two examples. There are two types of loads that can have stable AVDs. Traversed address loads are easier to understand. These are loads that produce addresses consumed by address loads. They're also leaf address loads. They produce addresses consumed by data loads. But let's take a look at the first one first. Let's think about the case of a regularly allocated linked list. You have the first node allocated address A, and the node size is k. The second node allocated address A plus k, and the node size is k. The third node allocated address A plus 2k, and the node size is k. Dot, dot, dot. Now, a traversal address load loads the pointer to the next node whenever you're accessing the previous node, right? It's basically this, what you do. Whenever you write a program to do a linked list traversal, that's what you usually do, right? Now let's take a look at the execution of this load across this linked list that's regularly allocated. We're going to compute the address value delta. Address value delta, remember, is the effective address of the load minus the data value of the load. For the first execution, we're going to visit the first node. The effective address is loading this node, which is A, address of the node. The data value is the address of the next node, because node will load next, right? We're loading the data value, which is A plus k. And address value delta is minus k, right? Address minus data value. Let's now in the next iteration we go to the next node, right? The effective address of this load is now A plus k because we are loading the current node. The data value is A plus 2k because that's the pointer to the next node. And the AVD is minus k. When we go to the next node, the effective address is the address of the node, A plus 3k. The data value is the address of the next node, A plus 3k, and the AVD is minus k. And keep doing that, assuming everything is regularly allocated like this, you get minus k AVDs for this, for that particular instruction. So you have a stable AVD, and actually you also have a striding data value. Which means that you could use a value predictor for this also, right? You don't need an AVD predictor. You could keep track of the previous values generated by this load, and you could use a stride predictor. Striding data value because the stride is instance, the difference between the data values loaded by consecutive instances of this instruction is always k, right? Make sense? So you could predict this load in two ways. You could have an AVD predictor as I described it, or you could have a stride predictor that basically learns the stride for this load and always adds k to the previous value that was used for this load. Yes?
And where are you keeping track of the node that you're at? Is that in the cache that you're making for the...
So that's the effective address. You don't need to, so this is the effective address. Basically, just by looking at this instruction, you know its effective address, and you're predicting the AVD.
What do you mean by effective address?
When you execute the instruction, you compute an address, right? Load address.
Uh-huh.
So you know that address. You don't need to, so this is just an example that shows what's the effective address for this load. You don't need to keep track of the address of the nodes. When you execute this instruction, you do a load. The effective address is the address of the node. Make sense? So you're actually computing the address when you execute the instruction.
Oh, I see what you're
Yes.
saying. Okay. Yeah.
Okay. It's a very simple mechanism because of that. If you needed to keep the address of all these nodes, that's extremely expensive. Okay. Any thoughts? Any questions? Okay. Let's take a look at the other example, which is difficult to predict with a stride predictor. think about a sorted dictionary. And this is one example actually that's used in a benchmark called parser. You have nodes that point to strings, and strings and nodes are allocated consecutively. But the dictionary eventually is constructed in a kind of a random way. There's no relationship between different nodes. So this is, let's assume that this is a string. It starts at address C, it's allocated. And then string size is k, and the node is allocated at address C plus k. And another string allocated at address F, and its node is allocated at address F plus k. And then you have a pointer from the node to the string. And node contains a bunch of other information also, like left, right pointers. And then you keep allocating these strings, and eventually you form a dictionary out of these strings, which looks like a binary tree. And if you look at this, the distance between the string and the node is always constant, because you allocate the string first, allocate the node next, and the string is always size k. But because you sorted all of these nodes, there is no relationship between the addresses of consecutive nodes in any way. It's kind of random, assuming your input string is random. So when you look up this dictionary for an input word, what you need to do is basically you need to traverse the load and load the string, right? So you have a leaf address load that loads a pointer to the string of each node. This is kind of lookup function. You have an input word, and you start with a node, and then you basically have this recursion function that does traversal. And there's this instruction that basically loads the string using the node pointer. Let's take a look at the execution of that instruction. Remember, ED is effective address of that instruction minus the data value of that instruction. When you visit the first node with an input string, you first need to load the node. Its effective address is A plus K. And the data value is really A in this case, right? Well, I guess it's, I'm assuming that I guess A plus K is actually the address of the offset of the string over here. But you can imagine that it's not that hard to bridge that gap. Basically, the effective address of this instruction, when you visit this node, is A plus K. The data value is the address of this string, which is A. So your ADD is K. Now let's assume that you're traversing, based on the input, the traversal takes you to the right node. The effective address of this instruction in that execution is C plus K, the address of the node. The data value is the address of the string, C. And the ADD is again K. Let's assume that again, because of the word you're searching, you go here. The word doesn't match the string, so you keep going, you keep traversing the dictionary. The effective address at this node is F plus K, the address of the node. And the data value is F, address of the string. Now if you look at this again, you get a stable ABT. Because it so happens that this instruction is loading a string that's always allocated k bytes higher or lower than the starting address of the node. You have a regular memory allocation pattern. So you have a stable ABD. You can predict whenever you load this node, you can predict the address of the string, which means that you can parallelize these two cache misses. Assuming this causes entry to Runahead mode, you can parallelize this cache miss. Assuming these go to different locations, different cache blocks. The data value, if you look at this, is not predictable, because assuming that these are all at different locations, at random locations, there is no stride over here. So in this case, you can use an ADD predictor and parallelize these cache misses, or parallelize these loads, but you cannot use a stride predictor. Okay. Any questions? Pretty interesting, isn't it? So this is one example of a technique that takes advantage of regular memory allocation patterns to improve performance. There could be other techniques, but we're not going to go into that. Prefetching actually could take advantage of that also. You could use this for prefetching as well, but I'm not going to talk about that. So basically, how do you do this? Let's take a look at how you do this, and then we're going to finish up soon. The insight is that how do you identify these address loads in hardware? Remember, we were predicting address loads only. We don't care about data loads because that's not going to lead to an address later. How do you actually identify address loads in hardware? The insight is that if the ABD of a load is too large, the value that's loaded is likely not an address. Why? Well, it turns out pointers are usually allocated from a memory address range, right? So let's say you have this is your address. Usually what happens is top n bits of the address are the same for pointers because they're allocated from a similar region in the heap, right? Or on the stack. Right? So if you're actually loading a pointer, the effective address of the load, the effective address of the load that's loading that pointer is very similar to the data value that's being loaded. They have the same n bits at top, if you will, because they're coming from the same address space, the same parts of the address space. So you can keep track of loads that satisfy only this criteria. Right? This ABD is within some bounds, within some bounds of absolute max ABD. This identification mechanism eliminates many loads from consideration. This way, you can enable the ABD predictor to be small because you're looking only for these address loads. Another way of doing this is actually looking at your effective address and the data value after the execution, of course, and checking if the top n bits of the effective address and the data value actually match. If they're the same, and if this is actually a pointer, well, it's a pointer because it's your effective address, then you can guess with good certainty that this data value is really an address because the top n bits are the same. Now you could be unlucky and this could actually be a data value itself that happens to have top n bits the same with a pointer, but more often than not, that's not the case, assuming you have enough number of bits in n. Okay, so let me give you the performance of ABD prediction, and we'll conclude after that. This is, again, some other set of benchmarks that are very intensive in pointer traversal. Linked list. This is a minimum span tree example, for example. This is a tree benchmark. Bytonic sort. This is a traveling salesman problem. ... This is a terribly written benchmark, actually. This is a benchmark that's written, that could have been rewritten without the way it's written. Meaning, you could have re-optimized data structures and get a lot better performance. But there are programs like that in the world. But basically, this shows the performance of Runahead over here, normalized, or normalized number of executed instructions. If you add ABD prediction to Runahead, you gain about 14% performance benefit on these workloads. And most of the performance benefits come from this health, actually, which is a terribly written benchmark. But even if you eliminate it, there are a bunch of workloads that gain quite a bit. And you can actually reduce the number of executed instructions this way also, because you're eliminating this additional Runahead period, right? The number of executed instructions reduces by approximately 15% if you do this. Of course, this doesn't get rid of all of the loads. If you don't have loads that have regular memory access patterns, like we've discussed, you may not be able to parallelize the cache misses, and this mechanism doesn't do that. So there's a lot more potential. Remember, I told you that the performance improves by 25% if you perfectly do this. Well, this is getting only about 14% of it, right? Not 25%. Which means that there's more potential. Okay. I think I'll stop here. I'll leave you with the wrong path event slides if you're interested in that. We've discussed that, but I'm not going to cover the slides. Any questions? Any burning questions? Okay, I'll see you Wednesday then.